Thank you, Vivek, for the introduction. I don't know, am I audible at the rear? Right, so today I'm supposed to be talking about natural language processing. I must express my sense of indebtedness to the organizers of the CCBR workshop for having given me this opportunity to talk to you. I presume many of you are students, and therefore at any stage of the presentation, if you have doubts, please feel free to interrupt and actually let me know in case I'm not understood well, right? It is not possible, as you can imagine, to cover the breadth of natural language processing in 1.5 hours. We have a full semester dedicated. In fact, those of you who are interested, who are in IIT and want to take a course on natural language processing can take the course offered by me this semester. And even that course is essentially only the foundations of NLP. So in 1.5 hours, I can only attempt to give you a sketch of the main problems in natural language processing. So I had a kind of dilemma here whether I should be talking largely about solution techniques or whether I should be talking about the problems in natural language processing. And my personal bias has always been towards appreciating the nature of problems so that you can get motivated about the solution techniques, which is only possible once you understand the problem landscape very well. So most of my talk is essentially going to be around some central problems, and I'll also, in the passing, give you some clues about how NLP people have attempted solutions to some of the hard problems. So many of you might be coming from different diverse backgrounds. If you have a machine learning background, some part of it may be a little more easily understood than some others. But as I said, I have tried to make it as understandable as possible to you, irrespective of your backgrounds. So please feel free to let me know in case you have a doubt. So it's natural language processing, and you can see that there are two different ways in which you can actually interpret natural language processing. And the way in which we do it in language is typically by the use of parse trees. And many of you from computer science backgrounds would be comfortable with the notion of parse trees. These are just symbolic notations for conveying what we understand through pictures or through imagery. Okay. So if you take the phrase natural language processing, we say that the phrase is ambiguous because I could be saying that it refers to processing of natural language, which is what is conveyed by the first parse tree. So you can see natural and language, right? Typically this is called a noun phrase, right, which is sometimes treated as a chunk. And it is, I'm talking about processing of this entity called natural language, right? The second interpretation of the phrase natural language processing is to do language processing in a natural way, in which case language and processing come together to form a noun phrase. And natural is a way of doing language processing, right? Interestingly, both of these interpretations can be valid interpretations. For most of this talk, I'll be taking the first interpretation, but the second interpretation is of personal appeal to me because I also tend to work in a field called cognition, right, or computational models in cognition, in which we are interested in how humans do language processing as opposed to how machines do language processing, and then trying to essentially extrapolate some lessons from how humans do language processing to implementations that might be cognitively more sound than what we have today, right? So the second interpretation is the more cognitive side of the picture, right? How do we do language processing naturally? So in this context, I would just like to say that most of the traditional natural language processing, the applications that you find are, you might have seen several applications actually. Search engines is very common. Most of you would be using Google. And you would also have come across conversational systems, question answering systems. Many of you would have been familiar with different kinds of summarization techniques, machine translation techniques, information extraction techniques. So these are all different applications, right, we are familiar with. But there are also very hard problems which we have not been able to solve. For example, till date, we do not have even a very faint clue about how to essentially design a system that can recognize a joke, right? If you give it a few lines of text, to be able to say that this is humorous is something that we are not yet there, right? So that is precisely the point where you would essentially like to draw some inspirations from cognitive models. And when you really look at the harder problems, and jokes might not seem like a very great application domain. Why would you need machines to laugh at jokes? But you'll soon see, maybe in the course of this presentation, that unless you really solve the hard problems, and that can, I think you just have to wait for a few slides to essentially see why the hardness essentially translates to many other problems, which are of definite practical significance. The second context of how humans do language processing is going to be of interest when you really study such problems. Am I making sense, or is it fine? Is the space okay? Anything that is not clear? Okay. So as I said, I took a definite stand that I will focus on problems and not on specific solution techniques per se. And I start with this very famous quote by Dijkstra, which says that computer science should be called computing science for the same reason why surgery is not called knife science, right? So this is a very important message, I think, right? So we are basically saying that you can use the same knife to cut an apple, right? But we call it surgery when it is kind of used to dissect a patient, in which case you need some knowledge of the problem pathology, right? Or the anatomy, whatever, right? So the computer is a tool, but you need to know the anatomy of the problem. If you have a problem, you can treat it as a disease, so you should have some idea about the pathology of that. And to be able to characterize that problem across certain dimensions, to be able to say this and these solution techniques would be appropriate for that, right? Otherwise, solution techniques are actually quite easily available. If you open TensorFlow and this and that, right now there are abundance of. So when you become consultants in a field, you are expected to be understanding the problem pathology, right? Just like medicines are available at any pharmacy shop, but you need the doctor to do the diagnosis. So when you essentially become a practicing NLP expert, you are supposed to be doing the diagnosis, right? Whereas the tools are available. So I think there is a confusion in the minds of some people that quickly I'll essentially take a problem and map it to the solutions, and that's not the goal of learning NLP, right? It's about a very systematic introduction to the understanding of problems, the same kind of rigor that perhaps a medical practitioner goes through before he essentially even has the authority to prescribe a medicine, right? To even say that this tool is appropriate, right? So I am basically emphasizing on this because this is easily overlooked, especially in today's age when, tools are a lot more abundant than they were perhaps 20 years back. So I have a few slides which I kind of use generally to motivate discussions, but maybe for the sake of brevity, I'll omit this. But it is important to know that this gentleman, George Boole, started this idea that you can essentially take, do some operations on language, right? So he said that, I mean, he wrote a very phenomenal book, right? I mean, very, very influential book, rather, called The Investigation into the Laws of Human Thought, in which he essentially said that the kind of English sentences we use in our everyday discussion, right, or whatever usage. So those things could be essentially formulated in terms of logic, right, at least some of the very basic ones. And he came up, as you know, with the Boolean algebra, and that was the that was the point where we started thinking of language in terms of logic and trying to map, trying to essentially say, can we realize some aspects of language in logic? So here you see something expressed in logic, which essentially is the principle of non-contradiction. It says a thing cannot simultaneously be true and false. And that is the logical way of saying that, right? So if I can take an English sentence and if I can have a logical representation of it, maybe I can do something interesting with machines, right? I can do some kind of inferencing and so on and so forth. So you can see that natural language processing started far back than we actually think it started. Interestingly, the Geoffrey Hinton, who recently won the Turing Award for his contributions in the field of deep learning, happens to be the great grandson, I think, of George Boole. So that has been an interesting lineage, I would say, right? Okay, so personally for me, if someone asks me to study something, I would basically study it only. If you say you listen to me, I listen to you, provided whatever you are saying is interesting, right, or it is useful, right? If you say that it's a very nice thing, listen to me, it's a nice piece of joke, or I'll have fond memories of what we did several years back, I'll listen to you because that's entertainment, or it should be useful to me, right, whatever you're saying. I don't see many reasons why I should be otherwise interested in a discussion, right? So similarly for studying something, right, it should either be interesting or it should be useful, right? It turns out that NLP is both of these, right? It is useful and it is interesting. So that slide should come first, right? So why study NLP in the first place? Other than, of course, helping you get a degree and get a job, which okay, so let me get into the interesting part of it, right? So for a scientist, something is interesting because the problem, why is a scientist interested in something, right? It's a reasonably interesting problem to look at. Why? Because there is something to be done there, right? The problem is hard, for example, right? So I think I don't need to convey to you about the fact that NLP is useful. I already mentioned a whole host of applications that are possible. So I'm not getting into that. But the interesting part of it, right? So this is physics, right? So I'll just try to convey to you over a succession of slides that natural language processing can be harder than any of the fundamental sciences, right? Which should be good enough reason to study natural language processing, right? If you're studying a field and if you're convinced that the hardest problems in fundamental sciences need to be solved and yet something more needs to be done, then perhaps that's good reason to study it, right? It can keep you engaged for a lifetime. So let us do that. So this is physics, right? What does physics do? It takes an observation and it tries to find some laws that can explain that observation. So I see a charged ball, I find all the charge resides in the outer surface of the sphere, right? No charge resides inside this metallic ball. So there must be some reason for that, and then people find Coulomb's law, right? So what happens is, as you know, that most of the charges reside on the, all the charge resides on the outer surface because the charges like to be maximally separated from each other, and that's the lowest energy configuration, right? So that's the idea. Now, similarly, when you look at an English sentence, right, you like to say, why is this sentence grammatical, right? Why is this a valid sentence and something else not a valid sentence? And then people try to find out the laws that explain valid structures, right? So in the language of, in the language of language, if you like, what you can say is that this is a grammatical construct, right? The charges residing on the outer surface is grammatical, but charges residing inside is not grammatical. It's not permitted, right? So natural language processing, we say the word natural because that's also a natural phenomenon. So I have to study it, right? So what are the laws that say that this is a grammatical construct, this is possible, this is admitted by nature, but that is not admitted, right? Sue, John, hate is not admitted, right? So then people start asking questions exactly as physicists ask and then come up with the laws of, the rules of grammar, right? So a linguist is essentially a physicist in that spirit, right? So Chomsky is essentially putting on the hat of a physicist, if you like. Chomsky, by the way, is the name of the gentleman who came up with this very influential book called Syntactic Structures in the 50s, I think, and that laid the foundation, at least in the Western world, of a lot of what we know about linguistics. Obviously, in the Indian context, there was some contribution, which is often not appreciated as much, but should be, by a person called Panini, and I'm not getting into that. So the next is there's a bit of chemistry, which means that physics is not enough. You also need chemistry, which means that suppose I have, suppose I have an inclined plane, and suppose I have a ball that slides down the inclined plane, right? Now, physics assumes that there is no interaction between the ball and the inclined plane surface, but that's not quite true, right? It could happen that there is a chemical interaction. So physics is trying to abstract out the chemical properties of objects and say that I'm just assuming that they won't interact. So that's a simplified model. But a finer grained model is offered by chemistry, and that says there could be interactions, right? So similarly, in language, when we are saying Sue hit John, right, we are perhaps a little more liberal than we should be, right? When we say, anything noun phrase followed by verb phrase is a sentence, because that also admits things like not only man plays guitar, but also guitar plays man, which is syntactically correct, but not semantically correct. So when we get to semantics, we essentially are respecting the individual properties of these objects, right? We are saying that there are chemical properties, analogs of chemical properties, which might actually lead to behavior that's quite different from what physics would predict, right? So not all syntactically correct sentences, as you can understand, are valid English sentences. There's more physics, which happens when you get to a little more complex world, where you have here, I don't know whether this is readable from the rear, but I would apologize for that if it is not. But it is just a few sentences of English which talk about cricket. And the point is that none of the sentences have the word cricket in them, right? So, but someone who actually knows a little bit about sports or cricket can actually read it and conclude that it is about cricket, right? Now, the thing about this piece of text is that the concept cricket is not present explicitly in any of the words in the text, but it emerges out of interactions between these words, right? So there is something called an ensemble property, which essentially emerges out of interaction of these particles, if you like, right? So the particles are the analogs of words. And in physics, when you have a lot of particles interacting and you have ensemble properties emerging out of that, we basically, the very standard Newtonian mechanics models don't work, right? Even for three-body particles like Earth, Moon, and Sun, you essentially cannot do a very nice analytical treatment. Closed form solutions are not possible. So, when you have a gas chamber and you have a large number of particles, you basically see that there are some properties like temperature, pressure coming out of the gas chamber. And these properties, temperature and pressure, are not shared by any of the individual particles, right? Particles only have properties like mass and velocity and so on, right? So this is very, and I mean, the analogy is very clear, right? None of the words have cricket or ovals or anything explicitly, right? Maybe you can take a stronger example where none of the words essentially have humor in them. But when the words interact, humor emerges as an ensemble property, just like temperature and pressure emerge as an ensemble property out of interaction of particles. So when you get to that end, you essentially have very deep problems. There the parallel is with statistical thermodynamics. So when a movie is romantic, right? So you have several pixels in each frame of the movie. There are several frames of the movie which interact with each other. But more than that, the movie must interact with my mental model to kind of give rise to the sensation of romance, right? If a 3-year-old kid is looking at it, she may not conclude that that movie is romantic, right? So the mental model of the recipient is also important. So it is a very, very complicated problem, right? We are really hitting the hardest problems of physics here, where we have a large number of particles, by which the official way of declaring that is to say that we have a large dimensionality, and we have nonlinearity in the sense of very complicated interactions between these particles, right? So this large dimensionality and the degree to which you have nonlinearity in the interaction of these entities essentially give rise to complexity, right? And that's the way people behave. I mean, it's the standard way in science to kind of talk about complexity. And it's very clear that natural language processing is complex, right? I don't get into all these things, I think, in a short presentation, but it's important to understand that. Okay, let us stop here for this slide. Now, let us get into biology, right? So we have gotten into physics, chemistry, we have seen a little bit of this. We'll see now that language also has some very neat correspondences with biology, right? Actually, if you look at it, we are still in the realm of what we call natural sciences, right? We are having physics, chemistry, we are studying something that exists outside. And we are actually, the complexity of the problem is getting higher as we are moving from physics to chemistry to biology, right? And then we get into things that involve human beings, right? Physics doesn't deal with human beings, nor does chemistry deal with human beings, right? They're largely concerned about matter, right? So as we go from physics through chemistry, through biology, into the social sciences, we are essentially encountering more and more complexity, right? And that's why beyond a certain point, we are not having mathematical models, right? We are having neat mathematical models in physics, slightly lesser in chemistry, I think. So you still have to memorize a lot of things in chemistry, right? And as we get into biology, there is a lot more of doing this cramming up, right? The mathematical models simply just don't exist in the social sciences in that sense. I mean, they do exist, but for very rudimentary, in the rudimentary sense, I would say, right? I mean, anyway, so you can see the kind of layers that we are going through, right? And when humans are actually doing language processing and humans are actually laughing then at jokes, then we essentially have to model humans as part of a societal process, right? The way they have essentially evolved to be humans as they are. And obviously the complexity of that process is a lot higher than what we can mathematically perhaps even envision, right? So it's very important to understand that natural language processing in its full-blown sense is actually a lot more than just use of tools for essentially getting some problems done. Though, I mean, a lot of Facebook and Google and all of them are essentially sponsoring research at the short term because that kind of makes a lot of money. But I'm just kind of trying to sketch out the big picture, which is important. So what is the correspondence with biology? The thing is, if you have a seed and you have a soil, and if the seed meets the right kind of soil, then it fertilizes, right? And, sorry, it germinates, let's say. And you have some life form, right? Now, this is very analogous to actually the person who is laughing at a joke. So he is having the soil, he is having the substrate in his mind, and the piece of text comes in as a humor. That's the seed. And that seed germinates in the soil and gives rise to a life form, which is laughter, right? So that seed can essentially fall in a soil, in a rocky surface, and it may not give rise to a laughter, right? So the soil should be prepared for accepting the seed and essentially giving rise to that life form, right? So if you actually have to understand natural language processing, if you actually have to handle humor, then you will have to fundamentally address this basic problem in science: when do molecules become living, right? Which is an unsolved problem in science, right? Where is the tipping point, right? I do a configuration of molecule and suddenly I say that it is a living molecule, right? This has life and this does not have life, right? So when I just declared now that living is understanding, is analogous to understanding, right? Understanding means it's able to take a life form. Not understanding means the whole thing goes there and stays there in my mind. I cannot give expression to it. I'm reading something on chess. I've never played chess. So it just goes and it reads like a sequence of words for me. It doesn't assume life form inside my head, right? So that's this understanding has not happened. So is this analogy making sense? Is this clear? So by now it's clear that we are really, if you have to solve natural language processing, you have to solve all the fundamental problems of science, right? Very large number of GPUs, TPUs, very high processing capabilities won't help, right? Unless you actually have got the science right, correct? Are you all in sync with me? Okay. So now I claim that it is even harder than biology, right, by saying that, as I say it in social sciences, right, but here I am having this phenomenon of folding in, which says that if the brain were so simple we could understand it, we would be so simple we could not, right? Which means that the observer, right, unlike in fundamental sciences, till now, right, till biology, the observer, the thing we were observing was outside us, right? But now the observer is becoming the observed, right? So it's folding back in. I had the telescope outside and I was watching the stars. Now I am folding the telescope back in. The same thing is observing itself, right? So the problem has got really nasty now, right? So those of you who are interested should read Douglas Hofstadter, right? Gödel, Escher, and Bach, right? That book. And you should see about what the implications of this kind of problem are in the more genuine sense. Okay, so I just mentioned this, that nonlinearity and dimensionality are the two axes for talking about complexity. That's very standard. I have just used something that nonlinear dynamics people use routinely, and I have just put NLP stuff there to say that Boolean algebra is somewhere here where you just have a dimensionality of 2, 0, and 1, or true and false. Very simple operations, so it's linear. And as you move higher up, you have very complicated stuff like jokes and poetry, where you have large number of words which are interacting in highly nonlinear ways, right? What do I mean by nonlinear? Some of you who have not come from a signal systems background or haven't encountered a formal definition of linearity, I just mean that if I take a cup of tea and if I listen to nice music, then the effects add up, right? So it's linear. Whereas if I listen to two pieces of music that I like, then obviously the effects don't add up, so it's nonlinear, right? So the official way of talking about that. The right jargon is usage of terms like homogeneity and superposition, right? But I'm not getting into those things. It's peripheral to the current discussion. Okay, sometimes when we talk about text, we also use the term unstructured, right? As opposed to databases, for example, which are structured, right? So what is the meaning of the word unstructured? It needs a little bit of clarity. So structured means that from the structure, I have a very nice way of inferring the function, right? So a kidney, for example, the structure is revealing of its function, right? Whereas a brain, your brain and my brain might look on the surface very similar, but they may be doing very different things, right? You may be interested in music, I may not be, and so on and so forth. So when the structure is not indicative of the function, is not clearly indicative of the function, or is only vaguely indicative of the function, we say that the structure function correspondence is weak, right? So when we say text is unstructured, we literally don't mean that, we really don't mean that the text doesn't have a title, subsections and all that. It does have a structure of that kind, but what we mean is that the structure in this way it is written is not very indicative of the function that the text is going to carry out, right? Unlike a database, record, for example, where the semantics is much more clearly specified, right? So that's the meaning of the word unstructured in the true sense, okay? So I will skip this thing that there are applications. I just want to say that there is yet another interesting way of looking at natural language processing, which is in computer science, we say that there are only two objects, which are 0 and 1, 5 actions, right? Computer science, the language of computer science, irrespective of which language you are programming in, ultimately gets translated into binary, right? So that language has two objects, 0 and 1. There are only 5 actions that you need to do to perform anything, and that comes from the abstraction of the Turing machine. You can move left, move right, print a 0, print a 1, and so on. So those are the 5 actions of the Turing machine, and there are only 3 ways of combining things, 3 actions that you can do. For example, you can have a sequence, you can have a conditional, and you can have looping, right? Everything else can be built on top of these. For example, recursion, you can kind of club that with iteration and use looping, right? So anything that you do in computer science, you can do it using a language that has these things. Now, human language, on the contrary, has large number of nouns, right? Actions are verbs, objects are nouns, and so on. And the ways of combining are essentially the rules, right? So if you look at the machine, I have 2 nouns, I have 5 verbs, and I have 3 actions. And if I have natural language, then I have of the order of 1 lakh nouns, some 11,000 verbs, and an unknown number of actions. I say unknown number of actions because there are different grammars that have been proposed by different people, and they have different number of rules, right? There is a grammar, for example, by Tomita, which has of the order of 108 rules of grammar. I mean, no one has devised a grammar for obvious reasons that encompasses all different behaviors or all different kinds of phenomena that you see in a language, but these are all approximations, right? So I've just put a question mark there. Now, if you actually have to realize natural language processing on a machine, then essentially this picture might help, right? Is this ever possible? At the end of the presentation, I might actually dishearten you by saying that it is not possible. But you will have to wait for that, because when I say it may not be possible, you need to know what I mean by it, and you need to know why I say it is not possible. So you demand a mathematical proof. So you will have to be patient with me, right? So it might be that something else you have in mind is possible. So the it pronoun has to be disambiguated, right? Which is also a natural language processing problem. Okay, so is this fine? Okay, is anything that I said till now not understandable? Anyone has a question? Okay, So there are two things we do in natural language processing, natural language understanding and natural language generation. Understanding is taking a piece of text and constructing some interpretation within the machine to represent the meaning of it. Generation is taking some interpretation inside and rendering it into text. For example, I could have a plan and I could essentially try to render it into text. For example, someone might ask me a question who is coming here for the first time, how do I go from ICSR to the main gate? And I have a plan. Plan is essentially a sequence of actions, right? So in artificial intelligence, we have planning systems that can essentially generate this sequence of actions. Once I have generated the sequence of actions and I have represented it in a language, then I can render it into text, right? And that's generation, right? Similarly, time series, I might have some weather prediction system, and you might like mobile messages, phone messages on your mobile phone, saying how the weather is going to be and what the summary was like for last week. And I could take some records and I could generate that into text. Okay, so both understanding and generation are hard problems, right? But generally people tend to say that understanding is harder than generation, right? Again, all of these require a more careful explanation, because under which assumption this is true, but general feeling is that to understand a piece of text is much harder. And the analogy I have here is with aircraft landing and aircraft taking off, right? So any pilot essentially, or actually many of us know that landing is a much harder operation than taking off, right? When we have autopilots in aeroplanes, most of the thing is done by what is called fly-by-wire, which means the pilot hardly has to do much, right? I mean, obviously he is accountable for all the errors, because of which he is actually paid. But the point is, much of the taking off and there's not much turbulence, perhaps much of the maneuvering when it's in the air can be automated. Where the landing, it's very difficult to automate, right? So it's the landing where the pilot really has to, the manual intervention is needed. And that's primarily because landing has to be done on a very narrow strip, right? It has to be very precise, right? Whereas in taking off, you can essentially fly somewhere in the air, and if there's a small error, you can still kind of recover from that, right? The margin of error that's allowed when you're landing is much lesser. The same is true with understanding, right? When I am speaking something, I am having a very definite interpretation in my head, and I would like you to get exactly that interpretation, right? So understanding has very little tolerance for errors, right? Whereas generation, I have something in mind, and I might be having several different choices, different ways in which I can express it, right? And that's why generation is regarded as slightly, understanding is regarded as harder, but generation community would be very furious hearing this, because as I said, it requires a lot more than. Okay, so this is not a very nice slide, but in case some of you are carrying back slides for preparation, then I just noted a few points which might be used for reference, that natural language is much harder than programming languages because you have ambiguity. The same sentence can mean different things. Ill-formedness, all the SMS messages that you have. Context is very important. The fifth point especially is very important, which is world knowledge, right? So it is very important to understand that when I am actually talking to you, I am using natural language, I am just saying a sentence, but I am not telling everything that is required to process that sentence. I am essentially relying on all the background knowledge that you have in your head to essentially make sense of that, right? Because of which what we are actually communicating using words is only the tip of the iceberg, and what is actually required for bringing that alive, right, is much higher, right? Because of which this whole idea that machines can look at text and suddenly do something very exciting is essentially self-defeating. It doesn't work, right? Because the whole thing is not even contained in that piece of text, right? So how can machines suddenly look at text unless it is equipped with all word knowledge that is required to actually process it, make sense of text. So this is a very important point, because when we look at programming languages, this is, I mean, some of you might be able to see the point. Co-reference is essentially the idea of, pronominal reference, for example, pronouns referring. I just mentioned it. That's an example, right? So pronominal reference is a class of is a subcategory of a wider class of reference called anaphora, right? So the different kinds of anaphora, and I'll maybe, the jargon for that is not important. What is important is to see that there is ambiguity that can come. Ram hit Sham, he was in pain. So you have to know who is in pain, right? So that is the problem of anaphora, and in this particular case, especially the problem of paraphrase is different ways of expressing the same thing, and language also evolves on its own, right? So, okay, so classic problems in natural language processing, right? So first of all, when we are doing natural language processing in machines, we start with words, then we go to sentences, then we go to what is called discourse, which is a set of sequence of sentences, and we also deal with something called pragmatics, right? So this is the natural sequence in which we go, right? When we do deal with words, it's like talking about atoms, right? So words, we say, are atomic units of meaning, right? When we talk about sentences, these are like molecules, right? Several atoms coming together, and you can see the correspondence when you say H2O, right, is a molecule, right? So it's a syntactically correct molecule. If I say HO2, that doesn't satisfy the valencies, right? So valencies are analogous to parts of speeches of words. So words must have parts of speech, and the parts of speech must kind of fit together like a jigsaw puzzle, right? And so that is sentences. So there are some formal ways of talking about word meanings. So instead of telling word meanings, people just prefer to talk about things like lexical semantics. Lexical means pertaining to a word, semantics meaning meaning. Morphology is about the structure of words and how different word forms originate from, for example, root forms, right? Sing to singing is a kind of thing that we typically call, again, there are some jargon which is not relevant, but morphology is essentially, at least two very important classes are inflection and derivation, right? So inflection, you essentially retain the part of speech tag in most cases. So sing to singing is inflection, but if you say educate to education, then that might be considered derivation because we are moving from a verb to a noun. So all the different kinds of things that you do at a word level, that's morphology, right? I'm just very simplistic here. Actually, there are many languages in which morphology is a lot more complicated. Turkish, for example, right? It's almost like forming a sentence. So the very simple morphological rules really don't work there. And phonetics, obviously. So as you see, each of these actually give rise in AI to different areas. Phonetics, speech processing people, they spend countless number of years. All the Google devices that you have that can process speech, right? So that's one area. Part of speech tagging. How do you automatically infer the part of speech tags of words? Sentences, you have to worry about what is called compositional semantics, right? Lexical semantics is about semantics at a word level. Compositional is what is the semantics when words come together to form a sentence, right? And discourse is what happens when sentences come together to form larger units, right? So the problem that I mentioned of anaphora, or Ram hit Sham, he was in pain, that's the problem of a discourse, because you have two sentences and you have to figure out what he is. That's a simple problem that exists in the field of discourse. So obviously, as you can imagine, there are a lot harder problems when it comes to meaning and so on. Pragmatics is more of language in use, right? So if I am seated next to you in lunch, and suppose I say, is there water in the jug? It would be very unusual if you say yes and then keep quiet, right? I would basically expect you to pass the jug of water in case there is water, right? So language also has this thing that there is implicit action tied to things. And same for, do you have a watch on you? And you just say yes and keep quiet. Okay, so in artificial intelligence community, there has been a shift in paradigm from what is called rationalistic AI to what is called empirical AI, right? So I'll have to explain to you a little bit about what these terms mean, right? So in the 60s and 70s and 80s, around that time, people were mostly thinking in terms of symbols, right? How can I represent symbols and logic and logical operations, formal semantics, and so on? And how can I do interesting things using that, right? Maybe an example will help. Yeah. So this is an example of classical AI, right? Classical AI says that I have knowledge about the world, and I encode that knowledge in the form of symbols. So I have some representation language that could be propositional calculus, that could be first order logic or whatever, right? And I represent that knowledge, right? And then when I have a question, I try to use that piece of knowledge to answer that question, right? So when I have a natural language query, I will try to transform it into logic, a logical representation, which becomes then amenable to processing. And then I'll use standard methods of deduction, right, and arrive at an answer, right? So all the knowledge that you have about the world will have to be encoded in the form of symbols so that you can finally do something interesting with it, right? So that is the approach of classical AI, right? So the analogy here is that you have a tank on the top, right, which has water. So that is where all your knowledge is being stored, right? All the propositions, all the knowledge in the first order logic, for example, everything is encoded there, right? And what you actually want is to disseminate water at each of these taps, right? So this is what you want to do is inference. Actually, this also illustrates the term top-down, right? Water is flowing from the top to the bottom. So you can see that we call that top-down processing or goal-driven processing, right? It's driven by the goals, right? So this is the idea. And what was the disadvantage with that approach? The disadvantage was that this was excellent. I mean, if you can encode the knowledge in the world in the form of logical things and get things done, there's nothing like it. But the whole point was that someone has to fill in the tank. You can see people going up the staircase with buckets to fill up the tank, right? The pump was not there, right? So this is what we call the knowledge engineering bottleneck. So for any domain, acquiring that knowledge, which would be enough for actually doing some significant processing, was actually the big challenge, right? And that is where machine learning came in and said that we can actually have a pump which can help in knowledge acquisition, right? And you can see the title of that slide is Why Machine Learning, right? So what we do is, instead of top-down, we also rely a lot on bottom-up. And you can see the pump is actually acting bottom-up, right? It's taking water from the bottom to the top, right? So that's a metaphorical way of talking about top-down and bottom-up. But you can also kind of take a simple analogy about goal-driven and data-driven, right? Bottom-up is also sometimes called data-driven, and top-down is also sometimes called goal-driven, right? As humans, we use a combination of both goal-driven and data-driven operations. For example, when I'm packing my bags, right? Many of you may have come from cities outside Chennai, so when you will be traveling back, you will be packing your bags. So how do you pack your bags? One approach is to just take a sheet of paper and then list down all the things you are going to put in the bag, right? And how do you do that? You just think, morning I'll get up, I'll need toothbrush, toothpaste, and this and that and everything, and you just make a list. So that's goal-driven, and that's top-down, right? So everything is done in that way. Bottom-up means, purely bottom-up approach means I just keep looking around in my room, and then for every object I basically make a decision. Should I put it in the bag or not, right? So that's purely bottom-up. It's data-driven or driven by the objects that I'm packing, right? Obviously, as humans, we do neither of these two. What we do is we do some top-down, and then we also look around and see, is there something that I have missed out, right? We want machines also to do the same, right? Otherwise, they become inefficient, right? So this is to cut a very long story short. So if you have to hear the full story, then you'll have to attend my course, okay? So, but I hope I am actually understood at least, that I'm not using jargon and leaving you in the dark about what's actually happening, okay? There's another, another important reason why machine learning is being used, and that's because a lot of the knowledge that we have is actually non-conscious, which means that we actually are not aware of how we are using that knowledge. For example, I just look at one of you and I know your name and I say, for example, Vivek has introduced me today. I meet him on the road and I recognize him and I say, hi Vivek, right? Now, I do not I'm essentially capable of doing the job, but I do not know how I recognized him as Vivek, right? I cannot tell you. If you ask me what is the algorithm you used, I'm not able to tell you. And the difficulty with many of the systems is that unless I actually can tell you how I did it, I cannot program it, right? So machine learning is useful for a whole class of tasks where you know how, where you can do the thing, but you do not know how you did it, right? So and it turns out that the large, only a very little part of what we actually do, we can actually talk about. You can see the tip of the iceberg. That's the rational knowledge that we have. If you ask me, why are you carrying an umbrella? I can tell maybe because I suspect it might rain, right? So that's rational knowledge. I can explain. But there are different classes of knowledge which we cannot explain. So speech, vision, and all of these communities use machine learning to a large extent because vision I just explained, recognizing a face. Reinforcement learning, on which you will be having a tutorial sometime, I think, is also using machine learning because when I'm riding a bicycle, if someone asks me what is the algorithm you use, I can't tell, but I'm effective in doing that task, right? So that's also non-conscious. So this is sometimes called the realm of the physically conscious, right? I'm physically conscious, I can play tennis, I can play badminton, but I can't explain how I do it. There is also emotionally unconscious. So there are all different layers in which these exist, right? So I love someone can love his mother, but he may not be able to give explicitly 15 different reasons why he does that. In AI, we essentially have a huge problem when we encounter these non-conscious, right? And one effective strategy in certain problems is essentially to judiciously combine the top-down and bottom-up. The top-down provides me some structure, and the bottom-up can flesh it up a little bit, right? Without the structure, the bottom-up really needs millions of examples to get anywhere, and even then we are not really sure that it's guided in the right direction. So we do need top-down, but we also do not want the top-down to be impeded by the severe knowledge engineering bottleneck that we face. And that's primarily the reason why there has been a move from top-down to bottom-up. But, as I will shortly tell you, you should not abandon the top-down, right? And this slide is essentially about that point. So, this is a short puzzle for you. It will also give me a little break. What I want you to do is to look at this slide and tell me what these question marks should stand for. Should it stand for yes or no? Water bottle. this fresh water? Thank you. Okay, so what is it? How many of you think it should be yes? How many of you think it should be no? Okay. What is the status of the rest of you? You need more time, or you think it's not solvable? Huh? You think it's too hard? What is it? Are you silent because it is too hard, or because it is post lunch? What is the reason? Or whatever I am talking is of no use, in which case we can talk about something that is interesting for all of us. Because as I said, I don't like to talk about something that is not interesting or useful, right? So, okay, so the point is it's hard, okay? And the reason why I kind of gave this example is that this is what machine learners really see, right? When you ask a machine learner, right, when you give it a prediction task, you essentially give it some columns like this and ask it to predict what this is, right? And this fellow has no clue about where this is coming from, right? And it basically says, yeah, yes, no, just like most of us are in this room, right? The machine learner is only having a time advantage, and it doesn't have the post-lunch syndrome, right? But so it can speed up its operation, right? But then it essentially has the same dilemma, right? With this much of data, it can only say, yeah, maybe yes, maybe no, right? If it is doing a good job, right? But suppose, for the moment, that I just gave it a little more extra information, right? So suppose I say days late, the number of days by which someone was late. So this has now become a domain. I have now supplied the information about the domain, what these numbers really mean, right? Or what these symbols mean, whether someone has a medical certificate, and whether the term paper was accepted or not. Suddenly it becomes a lot easier, right? Why? Because the qualitative relationships between these column names, right, help us or guide us towards a certain direction. We know that if the number of days late is high, chances are it will not be accepted. If the medical certificate is not there, chances are it will not be accepted, right? So it guides us. So this is exactly the role of top-down knowledge, right? When I have provided that, I have essentially given it the top-down knowledge. Again, there is an official way, right? A more scholarly way, if you like, right? Sometimes people like to pretend that they are scholars. So I might also like to pretend, if I, though I may not know anything about machine learning. So the idea is that the official way of telling that is to say that top-down knowledge prunes the hypothesis space of bottom-up learners, right? What does a machine learner do? It takes a set of data points, for example. Regression is a machine learning task. It tries to fit a straight line. So there are infinite number of straight lines that you can fit, and it has to finally land in one hypothesis, right? So it essentially, machine learners essentially take some data, they are bottom up, they are taking some data, and they're trying to learn some hypothesis that explains these observations. And so they are faced with this challenge. And when you have effective top-down knowledge, that can guide the direction, that can essentially prune the hypothesis space. Okay. So whenever you have an NLP problem, right, the message is that try to see whether you have top-down knowledge which can guide this effectively, right? The solution techniques may be very different in different cases. So you might have, for example, an optimization problem, which is your key bottom-up element, and you might like to feed the top-down knowledge in the form of constraints in the optimization problem. Then it becomes a constrained optimization problem, right? So these are general solution patterns which essentially come from an appreciation of the problem. But these are very general problem level understanding that is required. If you do not have that, then you might be misled by this solution technique or that, right? Okay, there are various other ways in which you can actually inject top-down into bottom-up, depending on which model you are using, right? So that those details, some of them I cannot do justice to in a short talk. Okay. Okay. So I just want to also mention that, you know, the different phases like symbols, numbers as in bottom-up approaches, you have weights in a neural network and so on. They are very analogous to phases of matter, right, like solid, liquid, and gas. And kind of there are some triple points. There are some meeting grounds of this, right? There are phase transitions. A symbol can get translated into a set of weights in a bottom-up architecture and so on and so forth, right? So there are beautiful ways of picturing computer science or aspects in computing science in terms of physics and in terms of complexity of systems. Okay, there is also, this is one school of thought, I mean, regarding school of thought, top-down and bottom-up. There are also important schools of thought inside language. So there is one in particular that I want to emphasize, which is Rogershank versus Chomsky. So Chomsky was someone who believed in structures and who believed in also something called universal grammars. I cannot talk about all of that in a short time, but I think from the top-down, bottom-up perspective, it means that unless you have a good top-down apparatus already built into your heads when you are born, right, you would not be able to make sense of language, right? So Chomsky's idea was essentially that just like birds are able to fly because they are already endowed with wings and some basic apparatus for flying, right? Similarly, humans are endowed with an apparatus for processing language. That was one aspect. So there is a significant top-down that we already we are born with, and then the bottom-up essentially fleshes that up. So if we are born as into a Tamil family, then essentially that universal grammar adapts itself to suit the needs of Tamil. If you are born in some English-speaking family, it would be something else like that, right? Specifics of language. So the bottom-up is used for fleshing that up. Okay. I'm very crude in what I'm saying, and the simplicity is to be attributed to brevity of time, and also perhaps to my ignorance about linguistics, but whatever. That's Chomsky. And Chomsky also believed that structure is important. So in a very naive way, you can think that if I'm given 15 sentences in a sequence, then you would take the first sentence, you decompose that, you would kind of try to find out the parse tree, do some analysis, you take the second sentence, then you would have to stitch together the representations of each of these sentences to come up with the representation of the discourse. That would be a naive way of thinking about it. What Rogershank says is that this is not how humans process language. When you see a piece of text, you already have expectations about what is going to come. So suppose I am actually reading a piece of text about an airline crash, then just by looking at the headlines, I can essentially expect that I'm going to see the name of an airline somewhere. I'm going to see what the casualties are like. In fact, very sadly, I think today I saw some crash happening somewhere in Iran or something, Ukraine. I mean, the casualties and, and many other details, right? What was the source of the flight, what was the destination, and all of that. So these slots of what I am expecting would essentially be raised the moment I read the headline. And when I'm reading the story, I'm just filling in those slots. If I'm not able to raise these expectations, then my memory is not equipped to understand the text that I have at hand, right? So I cannot understand. So Shank actually brought memory into the center stage of language processing and said that unless you understand memory and how human memory works, you essentially have no clues about how you can do any amount of serious language processing, right? So all of Roger Shank's work on text understanding, deep text understanding, was essentially focused on memory. I mean, it essentially had memory as a pivotal component of that whole process. And so I will now get into some specific details in the next half an hour maybe. I'll just show you some glimpses of how things are done in natural language processing. So the first problem I want to talk about is meanings of words and how words are modeled in machines, meanings of words. So this is a very fundamental problem, and you can see some pictures here about people who have, like from Augustine to Wittgenstein, who have thought about how meanings should be modeled. I just want to say that the problem is complicated because suppose you, many of you might have heard about techniques like word-to-vec and many other approaches which are around for modeling meanings of words in vector spaces and so on. But I just want to say that it's very hard to kind of model meanings of words, because if you even take a simple word like drink, right? The amount of processing that we are able to do as humans on the word drink is phenomenal, right? So if I just drink water, you could be concluding that the tumbler is getting lighter in the course of drinking, and my belly is getting heavier in the course of drinking. Now, how do I convey that to a machine, right? When the machine encounters the word drink, all the different ramifications of drinking has to be immediately evident so that it can do some serious inferencing. If it has to do story understanding. If someone gives someone something, then the object is no longer with them. And so on and so forth, right? If I'm giving a tip at a restaurant, then possibly I was happy at what I ate, with my experience. And possibly some transaction would have happened and so on. And you would also have perhaps guessed that the amount I gave as tip is not as large as the amount I paid for the dish itself. And those are commonsensical things that we have as very default assumptions about the world. And in fact, for a machine, the first thing is to disambiguate the word tip and know that you are not talking about a pencil tip or a pen tip or something, right? And then start and then do all the kinds of inferencing, right? So again, the bottom line is that we do not know how to model meanings of words in machines as yet, but we are only having approximations that work well for practical purposes, okay? So there are basically three different ways in which you model meanings of words in machines currently. One is exploiting linguistic knowledge. The second is what is called introspective approaches. Introspective, the word means looking within. So if you are given a corpora and if you're only looking within the corpora to kind of find meanings of words, then you call that introspective. The first and the third approaches are things where you are non-introspective in the sense that you look outside the corpora. So you have large volumes of text, but you also look at dictionaries, which are linguistic resources. That's the class category 1. Or you look at encyclopedic resources, for example, Wikipedia, right, which is in the category 3, which is exploiting background knowledge. So 1 and 3 are non-introspective in that sense, whereas just looking at the corpora and trying to, like I'm reading some piece of text and I don't know the meaning of a word. I often do not consult the dictionary immediately, but I try to make out the meaning by looking at the words surrounding it, right? So the machine also can do that, and that idea is given that formal name, scholarly name, distributional semantics, right? Which means trying to look around and figure out what the meaning could be, right? So that's introspective, looking within. Okay. Again, my analogies should not be stretched too far. So looking within doesn't mean that I meet a piece of text, the word that I don't know, and I start looking inside me and try to find out meaning. I mean that looking within the body of text, right? Other words in the context, right? So I hope I am taken in the right spirit. Okay. So WordNet is a linguistic resource, right? Which means that it already has words and relationships between words, but it's more than just a dictionary, right? It is derived from a field called psycholinguistics, which is about language in process. So there are different views of language. One is language as product and language as process, how humans deal with language. So WordNet has words, and WordNet has meanings associated with words. So WordNet actually makes a very important distinction between form and meaning, and it comes up with a unit of meaning called synset, right, which means that different word forms can belong to the same synset. For example, love and affection could belong to the same synset because they have similar meanings, right? Similarly, it's the same word form can have multiple meanings. This is sometimes called polysemy, right? The word bank can mean a financial bank, or it can have be a river bank. So, I mean, a synset is a unit of meaning. So a synset can be associated with multiple word forms. Similarly, the same word form can be associated with multiple synsets. So that's the basic organizing principle. And then you have associations, semantic relations between synsets, right? You do not have semantic relations between words, right? You have semantic relationships between synsets. So you can see some of them. Hyponymy is a semantic relation, meronymy is a semantic relation, part of relation, is a relation, and so on. There are also lexical relations which are between word forms. So I say rise is an antonym of fall, right? But I do not say rise is an antonym of descend, because descend, ascend, right? Rise, fall. So these are at word form level, not at word meaning level, right? So antonymy is a relationship at a lexical level, whereas is a lexical relation, whereas the others are considered semantic relations. So finer grained things exist, and I'm not getting into details. With verbs, there are very complicated relationships. Once you have that with you, then you can use that for processing. For example, someone is looking for, I mean, I'm just typing a Google query, cat licking mirror, right? Because I have WordNet, I can also recognize that a Word document having dog licking or dog biting glass is relevant, right? Though dog biting glass and cat licking mirror share no words in common, right? I can infer using WordNet that they are related, right? So if you have a resource like WordNet, you can exploit it to essentially make search more sophisticated, and similarly for other applications, right? Modeling word meanings. Introspective approaches, right? Introspective, as I said, looking within the corpora. So what you do is you take a corpus, you split it into paragraphs, right? And suppose I infer the meaning of words from the paragraphs in which they occur. So suppose I see the word bike, and I see that it occurs in paragraph 1, paragraph 4, it occurs 2 times in paragraph k, and 1 time in paragraph k plus 1, and so on. Then I have a vectorial representation of the word bike. Similarly, I have a vector representation of the word wheel, right? So remember that each dimension of that vector space, right, corresponds to a paragraph or a document, whatever you like, right, some unit of text, right, and you can represent words as vectors in that space. And then once I have that, I can just compare two vectors using a very simple measure like the cosine measure, for example, right. I can see how close two vectors are in that space and come up with some idea about whether two words are related to each other, right. So that's an introspective way of doing it. What is the problem with this approach? It makes you fall asleep. Is it okay? Whatever I am saying, is it making sense? Or should I stop? Correct. So cosine is one of the different measures that you can use, right? So you can come up with many different measures, and it can be adapted to suit your needs, right? So your needs could be different. Should I keep talking or should I stop, or is this enough for you? What is it? I don't want to continue unless it is. Right, so context could be different. That may be one argument. So obviously, this makes some serious assumptions. First of all, I am taking a bag of words model, which means that I am essentially ignoring the fact that the words come in a sequence, there is an order, right? There is a syntactic structure of the sentences and so on, right? I'm just taking words in isolation, right? I'm just taking a document as a bag of words, as I call it, right? All the words that are there, and I'm just comparing bags of words. So that's how I'm comparing documents, and from that I get, flipping the side over, I can essentially make that a basis for comparing words. So those are assumptions that you might have, right? Right. So I have not made all the assumptions of the vector space model explicit, but those assumptions should be there. Other than those, yeah. Actually, you find a family of techniques that are inspired from this basic idea, right? This primarily comes because of a problem called the problem of circularity, right, which I just show in the next slide. Now, if I say two words are similar, if they occur in the same paragraphs, if I take the statement 1 and 3, right, then there is no problem, right? But if I take statements 2 and 4, right, then there is a problem, which means words are similar only if they occur in similar paragraphs, but paragraphs are similar if they contain similar words, right? Do you see the point, right? 1 and 3, there is no circularity, but 2 and 4, in which I am saying I can only infer two words to be similar if they occur in similar documents. But then documents are similar only when they have similar words. Then I have a circularity, right? Then where do I start? It's a chicken and egg, right? Right? Okay. So this slide is very fundamental, right? Because if you don't see this point, then you don't know why people have come up with very sophisticated techniques, right? There are a whole class of techniques. There is a technique called latent semantic analysis. There is a probabilistic approach. So there is a factor analytic route for solving this circularity problem, right? Factor analysis is a class of solutions for handling this circularity problem. And one example solution is latent semantic analysis. Probabilistic models, these are alternate formalisms for handling this circularity. A class is, one technique is probabilistic latent semantic analysis, which is the probabilistic version of LSA. And also later Bayesian models, some of you may have heard names of things like latent Dirichlet allocation and so on. All these sophisticated mathematical tools have arrived to essentially solve this circularity problem, right? And then the third approach is the PageRank style approaches, and solution technique is SimRank, right? So PageRank, many of you know, is Google's way of essentially assigning priors to web pages, right? So before Google, right, AltaVista and other search engines, they were doing an okay job, but what they didn't know about was authority of web pages, right? Is there a place where I can write? No. Okay. So there is a probabilistic way in which you can picture it, right? There is something called the Bayesian formulation, in which you can say the probability of a document given a query, right, is something that you want to estimate, right? Given a query, what is the probability that this document is relevant? And that, on the right-hand side, that is proportional to the probability of the query given the document, right, times the probability of the document, right? So the first term, the query given the document, is called the likelihood term, right? And the next term, which is the probability of the document, is called the prior. So the posterior is said to be a function of the likelihood and the prior, right? The likelihood term, the first term, right? Now you are having to focus really hard because I am in the dog's world. You know, the dog cannot write, so the dog has to remember everything, right? So I don't have a blackboard, so I also have to remember everything and tell you, and you also have to remember what I am telling, right? Without secondary memory, imagine life of human beings, right? Sometimes maybe on certain tasks, animals are better off than us because they are more used to using their primary memories. I, for one, cannot remember phone numbers. Okay. Sorry for the digression, but the point is, this is the point, right? The posterior has the likelihood and the prior. Now, the likelihood term, you can see, has this very appealing form of probability, and also a little strange, of the probability of a query given the document. What does that mean? This means that the document can give rise to the query, right? So this is sometimes called a generative approach, right? That the document can give rise. So the same document can give rise to different kinds of queries. Obviously, documents never give rise to queries, but what it essentially means is that the document can address several different information needs, right? So every web page can be accessed in multiple different ways, right? So it has the potential to kind of, so that's the way to look at it. And then there is a probability of the document. Now, AltaVista did not have a prior term. It just had the likelihood term, whereas Google was far, far better than AltaVista. Primarily, obviously, there were a lot of engineering issues, but also, the primary thing is that it brought in that prior. The documents have prior. Some documents are more important than others. The Microsoft document web page is more authoritative than my web page, right? So it assigns a measure of authority. So if some information is coming from a very authoritative web page, you tend to trust that more, right? So PageRank is a way of essentially assigning importances to web pages. And remember that this is independent of the query. The prior term does not have query. It just has P of D sitting there, right? So it does not have query. So irrespective of the query, just by looking at the hyperlink structure of the web, I can essentially arrive at measures of importances of web pages. How do I do it? I do it by using this basic observation that a web page is important if it is pointed to by several important pages, right? If your web page is pointed to by Microsoft, by Google, by everyone, then you are likely to be very important, right? So a web page is important if it is pointed to by several important web pages. Now you see that this particular statement has a circularity in it. Is this correct? A web page is important if it is pointed by several important web pages. But how do I know those pages are important, right? So there is a circularity. So to solve the PageRank problem, you already needed to solve the circularity problem. It was solved by using the power method, an eigen decomposition, right? And what happens when you are able to solve one circularity problem is that you can transplant the solution to handle another circularity problem, right? So you can take the solution that PageRank offered and transplant it to solve this particular problem. And that is the essential ingenuity behind the SimRank approach. It essentially took the solution of PageRank, says, hey, you already solved the circularity problem once. Why are you worried about this? Let's solve it this way, right? So that's SimRank, right? And I'll just show you the intuition behind, let's say, EM. Now, I actually started thinking, what can I do in 1.5 hours? So I started making very silly slides. And it is related to dimensionality reduction. Dimensionality reduction techniques are often, because you asked the question, the answer is only for you. I'm not expecting the rest of the audience, but dimensionality reduction techniques are essentially often unimode in the sense that you either take word, word, or document, document, and then do the processing, right? For example, principal component analysis is a dimensionality reduction technique. Similarly, in the discriminatory world, you have linear discriminant analysis, right, which are techniques for, so these are all a class of techniques from multivariate statistics, which are essentially looking at univariate data, unimode analysis, right? Whereas latent semantic analysis is a dual mode factorization, which means that all the unimode factorizations, matrix decompositions can only happen on square matrices, right? Term, term, document, document, and so on. When you talk about dual mode, the interesting thing is that you can use singular value decomposition, which can operate on rectangular matrices. Obviously, you cannot do an eigen decomposition on a rectangular matrix, right? Yeah. But singular value decomposition is something that you can do on. So you can directly take the term document matrix, which is a rectangular matrix, and apply singular value decomposition to determine the underlying concepts, right? So it is dimensionality reduction, but in a very different setting, right? Okay. So the tools have to be adapted for that kind of task. Yeah. So as I said, I drew some silly pictures, and this is a picture for the expectation maximization, right? So, and circularity, right? So this is the problem of circularity, right? This is an elephant, and I have to take the picture of this elephant, right? So how do I take the picture of an elephant? We actually do solve this kind of problem, except that we are not aware that we are solving some kind of circularity. So we have several cameras that we have positioned to take the picture of this elephant. Is this fine? And each of the camera is taking some image, and then we are combining these images in some way to get the picture, right? That looks like a reasonable way to capture. Now, the problem is that to know where to position the cameras, I know what the elephant looks like. And to know what the elephant looks like, I need to know where to position the cameras. Looks nice? Shall I repeat? To know what the elephant looks like, I need to know where to position the cameras. And to know where to position the cameras, I need to know what the elephant looks like, right? So what do? You start with some position, and you keep moving these cameras somehow, right? This is the heart of expectation maximization. Okay. Some of you may have seen k-means algorithm, clustering algorithm. How does it work? It has two steps, expectation step, maximization step. Maximization is determining the parameters. Parameters are what? Where you are putting the cameras, right? Right? Expectation is what? Assignment. Assignment means a part of that, the data set is being assigned to that camera or to that mean, which is the parameter, right? So part of the elephant gets assigned to this camera, right? So you start off with some initial parameters, which is your M0 step. Then you do an assignment, which is your E1 step. Then you go to M1. Keep cycling through these steps till you finally arrive at some solution, right? So probabilistic techniques essentially mirror this basic idea, though, I mean, as I said, these slides were essentially made for brevity. I would never be using that slide for introducing expectation maximization, truly. But just to get a feel for what it is like, that we are actually dealing with circularity in the real world. So it's not that circularity is that uncommon. And in the whole process, we are actually assuming that the elephant doesn't keep moving, which would make problems even worse, right? So we are assuming a fixed data set, right? Now, when the elephant starts moving, then you get into even more difficult problems, right? And right now you have what are called quantum models in information retrieval, right? Where the observer has a particular influence on the observed, right? So the document actually keeps changing a little bit based on how you look at it. Obviously, the document doesn't change. The sequence of words remain the same. But the underlying experience that is being modeled by the document, or the semantics that is being conveyed by the document, is essentially a function of how it is being observed, right? So this is some really interesting stuff, Reisbergen. And over the last 1.5, maybe 2 years, I don't know, 1.5, 2 years, I have been working partly on some of these quantum models. I mean, well, honestly speaking, my student has been working, but that's the way I pretend that I am also doing something. But this is the idea. Okay, so things can get more complicated. Okay.
How do you know that you actually solved the circularity? Like, if you don't know what is important, how will you know you actually reached something important?
Very good question. How do you know that you have actually solved the circularity problem? Actually, in the case of expectation maximization, you may never really know. Okay, actually, if you see the actual form of the expectation maximization algorithm, it's essentially an optimization problem, and you are trying to maximize likelihood, right? There is some observation, and there is some underlying model which must have given rise to that observation, or so you hypothesize. So the model has some parameters, and you are trying to estimate the parameters, and you are saying that under these choice of parameters, you are most likely to have generated the observation that you are trying to explain, right? Now, when you are trying to maximize this, you essentially say that this is a, you are trying to maximize the likelihood, right? Or log likelihood is the. So suppose you plot the log likelihood, and if you see the landscape, you will find that this is a very complex form, right? If it actually had a very simple form in which you have a very nice convex optimization problem, then you would not have gone through all those difficulties. So because it has a very complex landscape, therefore, what expectation maximization really does is it only takes you to a local minima and stops there, right? It only says that the parameters have converged, right? So EM has a guarantee for the parameters to converge, but it does not have any commitment on having attained the global optima, right? So that's a limitation of the expectation maximization algorithm. I'm very glad you have asked this question. But so all you can really do is essentially have different starting points and hope that with different starting points, you essentially come closer and closer to the global optima, right? So I can initially start with this camera configuration and then start with a completely different thing. And I might actually land up somewhere completely differently. But in each case, I'm assured of convergence, right? Then I take the best solution, and then I kind of, okay. Best, again, in the sense of having maximized your likelihood. Okay, so that's the deeper story. So I had a few things about syntax, but I presume I have run out of time. Again, the slides were at a very elementary level, not to get too much into the technique unless you are asking questions, and unless I have the capability to answer those questions. But this is where the thing is. So, I mean, I don't know what is the schedule. Who is fixing the schedule? Can I take 5 minutes, or is it over, or what? I can take 5 minutes. Okay. So I will just conclude the thing with a little bit of syntax and say that you have this problem that happy boy eats ice cream, and you want to be able to model that phenomenon in machines, right? So what does ability to model mean? It means that given a sentence, you should be able to parse it, right? So if you have an ambiguous sentence, it can have multiple parse trees, and you should be able to generate all these parse trees. and you should be able to say that this is the most likely parse tree. Okay, so here you can have this is sometimes called, I mean, this is what Steven Pinker, who is, I don't know, maybe disciple is the right word, of Chomsky, right? So anyway, this is an example from his book, The Language Instinct. If you read that book, you might get some nice feel about formal structures of language. So I mean, is that apparatus enough is what he's asking. So suppose I say either the happy boy eats ice cream or the happy girl eats the ice cream, then can I still use a word chain, right? If a word chain is good enough, then I'll use that as a device for modeling syntax. But it turns out that this is not enough, because either can be followed by or, if can be followed by then, but either cannot be followed by then. So I need to be remembering something, right? So one option is to say, okay, I'll make the word chain more complicated, and then either will be followed by or, and if will be followed by then, and then it can handle. But as you take more and more sentences, the thing soon runs out of hand, right? And it turns out that you need an infinite number of such word chains. Again, the technical term for that is finite state automata, but you need infinite number of such entities to essentially model syntax. Okay, so what and this phenomenon is also sometimes called the phenomenon of center embedding, and you can see that this is a complicated sentence where you'd see the need for this memory, right? That you need to keep a record of what you have seen before, and long distance dependency, right? So you can see how can ties with escape, claim ties with maybe that, and so on. So, so when you have such complicated phenomena, you need an apparatus which is called context-free grammars, and an associated device called the push-down automata. And you have things like recursion in the rules, right? You see verb phrase reducing to verb phrase. You see the third rule over there. That's very illustrative, because you have a verb phrase to the left and you have a verb phrase to the right, right? So these are typically called production rules, right? I am assuming that most of you are familiar with that. And these are the two different parse trees that can come out of the sentence deep I ate noodles with chopsticks. And as you can see, one of them I think the first one is a bit of a funny interpretation, where the chopsticks are eaten up along with the noodles, which is the wrong interpretation, and this might be the right one, right? So a typical top-down classical parser basically has this challenge of generating all the parse trees and selecting from them. In contrast, the bottom-up parser is a monolithic unit. It essentially takes the sentence and it generates all the parse trees and assigns probabilities to each of these parses, right? So this is the idea of probabilistic parse trees. So I have some slides on probabilistic parsing. Maybe I'll skip. But you can see that in probabilistic parsing, each of these parse trees are essentially assigned different probabilities. And the rule probabilities that are required, right, are induced from the corpus. So there are methods by which you can essentially use the same kind of techniques like expectation maximization to essentially figure out what the probabilities should be. So the probabilities are like parameters, just analogous to the parameters that we saw in the clustering example. So I want to conclude by saying that I mean, syntax and semantics, though they appear to be very different, there are the boundaries are not that crisp, because if you actually take words and have deeper level representations, more fine-grained representations of how they behave, then you can actually do everything with syntax, right? But that's not practical, right? Because you'd have a huge number of part-of-speech tags, actually as many part-of-speech tags as number of words, for instance, which is not a practical thing to do, right? But the conceptual thing that it is in a spectrum should be made clear. Harder problems are Winograd schemas, where this is a typical question that is being asked. A trophy would not fit in a brown suitcase because it was too small. What was too small, the trophy or the brown suitcase? So this is a problem of anaphora resolution, finding out what was small. And you see that that requires a huge amount of background knowledge to be able to solve. The state-of-the-art performance on such tasks is abysmally low. I think the Ichkai 2017, is it, or whatever, very, very recent Ichkai, I think around 50%, and that too using crude methods, I think. So that is where the hard part really is, to be able, so any of the problems that you take, you'd have encountered this harder end very soon, where you essentially need cognitive agents to be able to deal with the entirety of the problem. And I had a final slide where I tried, as I kind of promised that I'll conclude that certain problems are unsolvable in language because certain things cannot be expressed in language at all. And this is the Wittgenstein stuff, which says that not everything that you have in the world can be expressed in language, and those are the limits of natural language processing for obvious reasons, right? So if I'm having an apple, and if I point to the apple by using the word apple, the connection between the word and the object apple is not contained in the language itself, but you need a separate language to establish this connection. But that language again would have the same problem, in that the signifier and the signified would not, the relationship between the signifier and the signified would not be contained in that language. So language fundamentally is not self-contained, so you need an infinite recursive language to essentially make it a self-contained system. And that is Wittgenstein's primary logical argument as to why you cannot essentially express everything in language, and therefore there is always something that will perhaps take you to the reign of the mystic, right? So with those few lines, I'll conclude